Hey everybody, welcome back. This is Math 35, College Algebra at College of the Sequoias. And today we're going to continue talking about our basic graphs, but now we're going to do some translations and shifts with them. So section 2.7 is on translations. Translations of graphs. And it's not like translating a language where you're converting one language to another. In graphs, what we're doing is we're converting the graph from one position to another. So we're changing its position, maybe its shape a little bit. So recall y equals x squared. And we had our delta x and delta y. Well, maybe I could just say x and y for now. Okay, but the reason why I say delta x and delta y is because it also represents a shift. What I'm doing is I'm just going to plug in some numbers. And when I plug it in, what I'm doing is I plug in numbers of x, I'm calculating y. So y equals x squared is negative 2 squared is 4. Y equals negative 1 squared is 1. Y equals 0 squared is 0. Y equals 1 squared is 1. Y equals 2 squared is 4. These were our shifts, and we talked about these before. This one's the center of the graph. Center, or vertex for a parabola. Like such. That's what's happening there. What happens if we modify the graph, though? What if we change the equation? Take a look at y equals 2x squared. We're going to do a similar process. Now, 0, 0 hasn't changed. Plug in 0, you get 0 out. What's going on here, though? If we do plus or minus 1 and plus or minus 2. Well, if I just treat this as x squared, let me make a column for 2 times delta y, or 2x squared. When I stick in y equals plus or minus, or x equals plus or minus 1, I get y equals 1. When I stick in plus or minus 2, I get y equals 4. But then I have to double it for the 2. So 2 times, this was x squared. Maybe that's a better way to put it. This is x squared. It's y equals x squared equals 1, and x squared equals 4. I want 2x squared, though. This is still 0. We double this, this is 2. And we double that, and that's 8. If I put that on the same graph up here, I can try. The center, the vertex stays the same, but now what I've done is I've moved, all my y values have doubled. So I go over 1 up 2 from this line, and I go left 1 up 2. And same for this, I go left or right 2, I go up 8. There's a couple ways that this is looked at. Whenever we have, this is, I use y equals 2x squared, but if we did a general form, y equals 8x squared. And if a is greater than 0, we have what's called vertical stretching. That's what happened here. Actually, let me change that. Let's say A is greater than 1. Oops. A is greater than 1. If A is greater than 1, it stretches upward. All the values, the Y values, stretch upwards. Okay? If A is less than 1, or between 0 and 1, I should say, where A is a fraction, we have vertical shrinking. And I can do that real quick. I can illustrate it here real quick. Let's take a look at that. Let's say we had y equals 1/2 x squared. My zeros haven't changed. But plus or minus 1 and plus or minus 2. When I do it, this is 1/2 plus or minus 1 squared is 1/2. This is 1/2 plus or minus 2 squared. Plus or minus 2 squared is 4 times 1/2 is 2. So whenever we go left or right 1, we only go up 1/2. And whenever we go left or right 2, from the change in x, we only go up 2. And so they call that vertical shrinking because it's gone, all that y values are going down. That's the general idea of what we're going to be doing in this chapter. We're going to be putting values in front of a or x squared on different graphs, seeing what happens with them, what happens when they're negative, and then what happens to the equations when the graph is shifted to a different location. So what we're going to be looking at here, for a function f of x, we're going to look at y equals a times f of b x minus h, like that, parentheses, plus k. Where y equals f of x is the base graph. And a was just like we had in y equals x squared. A in front does the following. A greater than 1, get vertical stretching. And if you look at it, it makes the graph look narrower. And when we had a is between 0 and 1, we had vertical shrinking. And it makes the graph look wider. If a is negative, a is less than 0, we do the same stretching and shrinking, depending on if it's between or greater than or less than -1 or between 0 and -1, but flip the graph upside down. We'll take a look at that in a second. I'm just going to tell you what all of them do real quick, and then we're going to look at them on different graphs. That's A. What B does if b is greater than 1, it's horizontal shrinking. And if z is less than b is less than 1, we have horizontal stretching. And these are backwards from the other ones. Notice b greater than 1, a greater than 1 was stretching, b greater than 1 is shrinking. And I'll show you what I mean by that in a second. This makes the graph narrower. And this makes the graph look wider. And let's take a look at h. So if h is greater than 0, the graph moves right by h units. And if h is less than 0, graph moves left h units. And notice it's up there, it's x minus h. So h is the opposite sign of what's in parentheses. For example, if we had x plus 2, this is the same as x minus negative 2. To make this match up, we've got x minus and x minus, which means h has got to be negative 2. It's the opposite sign of what you see here. Same thing if this is negative, this comes h is positive. Finally, we have k. K is pretty easy, and k is straightforward. If k is greater than 0, the graph moves up k units. If k is less than 0, the graph moves down k units. And I'll show you, I'm going to show you, let's start with the k. K is probably the easiest one to take a look at. So we're going to do y equals x squared, and we're going to do y equals x squared minus 4. This is effectively having k equals negative 4, which means our graph is going to shift down 4. And just make a little table and show you, and then we'll do it pictorially. Those were our things for x and x squared. And if I subtract 4, x squared minus 4, I'm just subtracting 4 from this. This is 0, negative 3, negative 4, negative 3, 0. And our base graph, y equals x squared, is right there. And if I plot x squared minus 4, I literally, all I was doing is plugging these in, squaring, and then subtracting 4. Negative 1 squared is positive 1. 1 minus 4 is negative 3. So my origin, the vertex, is now at 0, negative 4. And I've got a point at negative 1, negative 3. I've got a point at negative 2, 0. I've got a point at 1, negative 3. I've got a point at 2, 0. What's changed here? All of these are down 4 units. So if you remember the base graph, change in x, change in y, we have plus or minus 1 is 1, plus or minus 2 is 4. Move your center down, move your center by k units, and then plot points from there. Do the same one, y equals x squared minus 4, to illustrate what I mean by that. So if I go down 4, the origin was here, I'm going to go down 4 units. And if I do my plus or minus, if I go left or right 1, I go up 1 unit. Right 1, up 1, left 1, up 1. And if I go left or right 2, I gotta go up 4. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. On graph paper, that would look a little bit better. But here, I had to do calculations. Here, simple shift by k units. And use my pattern for x squared. Let's take a look at h now. We'll do the same idea with h. We're going to do y equals x squared again, and then I'm going to do y equals x minus 3 squared. So if I make this look like x minus h, then the minuses x matches up, minus matches up, means h has got to equal 3. This means h is greater than 0. We're going to move right 3 units. So let's just do that. Again, x squared, delta x, delta y, plus or minus 1 is a change. Left or right 1 is an up 1. Left or right 2 is up 4. H is 3. I'm going to move my center right 3 units. Let's start with the center. It was here. I'm going to move it right 3 units and put it right there. 1, 2, 3. And now I'm going to follow my pattern. Left or right 1 from there. I go up 1. Left or right 2 from there. I go up 4. And you don't need to do this, but I'm doing it just to show you that how it works. This point right here is 4, 1. This point up here is 5, 4. And here, 1, 2, up 1. This is 2, 1. This is 1, 4. And the vertex is 3, 0. If I make a little table of x and y, I've got -2, actually, I don't want to look at the -2. That's going to put me way off the graph. I didn't even look at x equals 0. Let's start at x equals 1. Actually, I'm going to illustrate that. Let's do the -2. 1 and show why this sucks. The -2, I've got -2 minus 3 squared. -2 minus 3 is -5 squared is 25. I don't want to plot -2, 25. In fact, I'm going to do that on another page. I think having them in order is better. Now, on our base graph for y equals x squared, we did -2, -1, 0, 1, and 2. If we try that here, -2 minus 3 squared is -5 squared is 25. -1 minus 3 squared is -4 squared is 16. Zero minus 3 squared is -3 squared is 9. 1 minus 3 squared is -2 squared is 4. And 2 minus 3 squared, -1 squared is 1. I'm going to show you what that looks like. We're going to actually, it's going to be a pain in the ass doing it. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Maybe I should make these a little bit narrower. The x and y look like the same scale. 1, 2, 3, 4, 5. And that's -5. So if I just do these 5, I'm going to do these 5 in red. These are the ones we started with. Our normal 5 points, normal 5 x's for y equals x squared. I've got negative 225 is way up here. Negative 116, 5, 10, 15, 16 right here is right there. 0, 9, that's 10, so that's 9 right there. I got 1, 4, and 2, 1. That's what plotting the base 5 gives me. Do the base 5 points that we use. Show that it's a parabola? No. But if we focus on the points that we have in our graph, here we had 1, 2, 3, 4, and 5 as our x values when I shifted. I've already got 1 and 2. I'll redraw them down here. There, 1, 2, 3, 4, 5. If I stick in 1, we already did that. 1 minus 3 squared was 4. 2 minus 3 squared was 1. 3 minus 3 squared, 3 minus 3 is 0, 0 squared is 0. 4 minus 3 squared is 1 squared is 1. 5 minus 3 squared, 5 minus 3 is 2. 2 squared is 4. These 5 show that it's a parabola. These 5 reveal the parabola, I should say. And I'd have to keep plotting. 3, 0. And now we see it. Using the base 5, though, doesn't show it. And I can tell you right now, I see it often. This is what happens. Often, students don't understand that the shift, how to use the shift. So they'll graph the base 5, and they'll show this line. And since they almost look like they're in a straight line, if we just looked at the red, I mean, I put a little curve to it because I knew it was a parabola. I could, especially not on graph paper, I could try to make that look like a straight line, and it would do not too bad. And so I get something that looks like a straight line, and we know it's a parabola. So it's easier to do that shift by 3. It's better and easier to shift over, and rather than saying 3, I'm going to say h units and plot points from there. That doesn't mean you can't use the table. If you like the table, use the table. Okay? I'll put that on another page. Moving the center or vertex HK, H units and K units. The H is left or right. K is up or down. Is a great starting point. Then plot points that follow the pattern of the function, pattern of the base function. Alternatively, and this is what I was saying on the last page, make your center start at HK, x equals h. When you plug it in, you're going to get y equals k. You plug in h, doesn't matter what it is. A times f of b times x minus h plus k. X minus h minus h equals 0. It's going to make that function part 0. For any of the base graphs, that's 0. So you just end up with k. So start at x equals h and go 2 left and 2 right. And right 2. This is like h minus 1, h minus 2, h plus 1, h plus 2. Now that may look funny, but let me go back to pointing out what we did with the y equals x minus 3 squared. H here was 3. So I put the 3 there. I go h minus 1 is 2, h minus 2, 3 minus 2 is 1. So I'm literally just going left 2 and right 2. And don't overthink this part. You don't need to memorize those. Just subtract 1 or subtract 2 from each one and add 2 from each one. Okay? We'll look at some more. To show some more what's going on. On this one, we're going to do y equals f of x. The base graph is going to be absolute value of x. And let's take a look when we have a negative in front. What about when we have negative absolute value of x? This is like saying y equals negative f of x. Because this part here is f of x. Right? So I can rewrite that as y equals negative f of x. So when I had the y equals a times f of b x minus h plus k, it looks like here this negative has got a little match up with the a. A equals negative 1. It should go downward. I said negative values for a go downward. Let's take a look at that. Let's see if that holds true. So let's look at y or x. Y equals absolute value of x. Y equals negative absolute value of x. The 2, negative 1, 0, 1, and 2. And when you stick x in and make, no matter what sign, if you stick it in the absolute value, it makes it positive. So 2, 1, 0, 1, and 2. And now I want to do the negative versions of those. I'm just taking what I had in this column, multiply by negative 1. I get negative 2, negative 1, 0, 1, negative 2. So my base graph is that one. Y equals absolute value of x. When I do the reflection though, or the negative absolute value of x, I've got the point -2, -2, -1, -1, 0, 0, 1, 1, and 2. Not sorry, not 1, 1, 1, -1, and 2, -2. It's going downwards. So that part is y equals negative absolute value of x. We call these reflections. This is a reflection across the x-axis. Take a look at another one. Let's have our base graph be y equals x cubed. So f of x equals x cubed. And then we're going to look at y equals, I'm going to put negative x in parentheses, negative x cubed. So this is like f of negative x. What I have there, got to match that. So it's negative x there. So when we were looking at f of b, x minus h plus k, and we had a out front, the negative sign is inside. It's multiplying by the x, so it's got to be the b. B is -1. Okay? When b is negative, if b is negative, we reflect across the x-axis. Or y-axis, sorry. You remember on this one, for x cubed, we did this in the last section, plus or minus 1 led to plus or minus 1, and plus or minus 2 led to plus or minus 8. That's for y equals x cubed. If I want to do y equals negative x cubed, when x is positive 1, I'm making a new table, not just an extension of the old table. When x equals 1, we get y equals -1 cubed is -1. And when I plug in x equals -1, we get y equals -1 cubed. Negative is positive. Positive 1 cubed is 1. So on y equals negative x cubed like that, we've got the point 1, -1, and -1, 1. But on our base graph, y equals x cubed, we had 1 leading to 1 and -1 leading to -1. The same thing happens with the 2 and the 8. So y equals x cubed That's our base graph. I've got 1, -1 is up here, and oops, 1, -1 is down here. -1, 1 is there. If I do 2 and -2, this is going to spit out -8 and +8 when I put it in here. So if the y-axis is like a mirror, it acts like a mirror. Whatever's here, this is 2 units out. We're going to reflect it and go 2 units that way. So it just reflects across. That's a distance of 1, so we're going to put a point over here going a distance of 1 there. Another way, oddly enough, on this one, I could write this as y equals, if I write that out, that's just y equals -x cubed if I get rid of the parentheses. And if I write it like that, y equals -x cubed, we've got a equals -1, and that has a vertical reflection. That reflects across x. So that reflected downward, that reflected downward. Y equals x cubed is one of the special ones that does that. It does reflects across both when you stick it -x. All right, let's talk about symmetrical graphs. Symmetrical graphs look the same when they are reflected across a given line called the axis of symmetry. Axis of symmetry. Y equals absolute value of x, y equals x squared. I'm just drawing absolute value of x and absolute value of x squared graphs. In both of these, points on the, if I take a point on the left, however far across that is from the y-axis, I can go the same distance over here. So if this is like g units, then I would do g units that way. This line right here, use green. This is the axis of symmetry. It acts like a mirror. If I held up a mirror and looked at it, it would look like it's reflecting across. axis of symmetry right here is the only thing that's consistent along this line. Vertical lines have an x value, x equals 0. Same thing here. Axis of symmetry is the y-axis. X equals 0, or y-axis. If you look at, I'll let you pause that, put down what you need. All right. If we looked at y equals x to the 4, or y equals x to the 6, or y equals x to the 8, we will see the same symmetry across the y-axis. Let's see if I can load this up in a smaller image. Desmos. Actually, I'm going to go to our class, because I've got a link to it right here, and I want you to see it. Grabbing the link is an easy way to get to it. I'll do that. There's our thing. If you come down here, it says Desmos. Click on Desmos. Go to the external website. Let's shrink it back down now so you can see my writing. Start graphing. I'm going to do x equals 0 first. Oh, good, it's in red. Perfect. Y equals x squared. Y equals x to the 4. Y equals x to the 6. Oops. All right. Just look at them one at a time. If I do y equals x squared, we can see it's reflecting across this x equals 0 line. I look at x to the 4, doing the same thing. X to the 6, also reflecting across x to the 8. In fact, if you see them all at the same time, let's zoom in on so we can see 0. These are our base points: 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. Notice it kind of widens it, going to x to the 4th, it widens it right here and narrows it right there. If I compare x to the 4th and x to the 6th, there's x to the 4th, x to the 6th is the same thing. It widens it between 0 and, or negative 1 and 1, and it narrows it between outward of that. And looking at x to the 6th and x to the 8th, same thing. In fact, it looks like it kind of like flattens out near the origin. Having all of them on there though, a little confusing, a little hard to read. But what do these graphs have in common? What these graphs or what these equations have in common is that x has an even exponent. So if y equals x to the n, and n is even, we will have symmetry about the y-axis, or x equals 0. That's y equals x to n. Y equals x to the n is part of a broader category called an even function. When n is even, it's part of a group called even functions. An even function has the following property. So property of even function normally we have f of x. If I put in negative x inside it, it has the same value as y equals f of x. That's what makes a function even. Notice this worked in when we had y equal the absolute value of x, which is f of x. If I stick in negative x, that's f of negative x. But absolute value of negative x is the same thing as the absolute value of x, which is f of x. So f of negative x equals f of x. You can look at the same thing with y equals x squared. That's my f of x. If I make this f of negative x, I replace x with negative x, and you need to do it in parentheses. But that's the same thing as x squared, which is also f of x. So this is true with, these are the even functions. And even functions are symmetrical about the y-axis. What am I sharing right now? Did I share screen or did I share? Let's reshare that. I want to make sure I'm sharing the whole screen. I don't think I was, so I want to talk about the Desmos again. So if we're in our Canvas course, and you click on Desmos, and you open it in a new tab, it's going to take you to Desmos. I plotted x equals 0 as a red line, and then this is y equals x squared. It's symmetrical about the x-axis, or y-axis. Y equals x to the 4th, also. Y equals x to the 6th, also. Same thing with y equals x to the 8th. And what I was trying to show earlier is when we raise that even exponent, look what happens. See, between -1 and 1, the graph gets kind of wider. Instead of being nice like this, it's more of a flat bowl rather than a valley. But between 1 going outwards, it now narrows down. That's what I was trying to say earlier. I don't think you were able to see that though. That's symmetry about the y-axis. And there's an easy test for it. Easy test for symmetry about the y-axis. About either axis, about the axes. If we're symmetrical about y-axis, replace x with negative x. If it's the same as the positive x, it's symmetrical about y. And if I want symmetry about the x-axis, here we're going to replace y with negative y. So this is what I mean by doing the test. Example. Y equals the absolute value of x minus 3. I'm going to replace x with negative x. If I do that, absolute value of negative x is x minus 3. Absolute value of x minus 3 like that. This is the same. So if I say this is y equals f of x, and I plug in negative x, I get the same thing as positive x. That's what I was saying earlier. That gives us symmetry about the y-axis. And if we looked at the absolute value of x minus 3, it looks something like that. What about if I replace y with negative y there? Leave that graph up there, just because it's handy to see that it's not true for the other one. What about y for negative y? So y equals absolute value of x minus 3. If I make this negative y, I can rewrite this, multiply both sides by negative 1. I get y equals negative absolute value of x plus 3. It's not the same. So f of negative x does not equal f of x. It's not symmetrical. I'm sorry, not f. It's not the same, so it's not symmetrical about x-axis. And we can see that here. This is the x-axis. If it was symmetrical, I should have, it would look like a diamond, wouldn't it? Just looking at the center part. that was reflected up, it would look like a diamond. It's not. What about x equals the absolute value of y? Go ahead and try to figure that out. I'm going to show these real quick. Oh, make that -3. So we can see absolute value of x minus 3 is there. And negative x minus 3, it's got the same symmetry. In fact, it looks the same. It's identical to y equals x minus 3. Let's see if we can do it with that one. X equals absolute value of y. Absolute value of negative y. So looking at these, it looks like plugging in negative y results in the same graph. So if I tried symmetry about y, replace x with negative x. If I do that, I got negative x equals absolute value of y. That doesn't even work. Absolute value of y can't be negative. In fact, what happens if I try that? Negative x equals absolute value of y. The only values that works for is when x is a negative number. See that? Comparing these two, though, they're not the same. When we said replacing something with a negative sign flips it across the axis. That's what it's doing here, but symmetrical graphs match. So if we draw this by hand, x equals the absolute value of y is like that. And this one is like that. It's a reflection that doesn't match the original graph. So it is not symmetrical about the y-axis. But if I do replace, if we look for symmetry about x-axis, we do y turns into negative y, x equals the absolute value of negative y, that turns into x equals absolute value of y. So back to the original graph, it's symmetrical about x. The x-axis. Which means if I go up certain units from the x-axis, I'll see the same thing. If I go down same amount of units with the x-axis. And we see that here. The graphs are the same. When I stick in negative y, I get the same graph. Which is another way of looking at it. In fact, graphically is almost a better way of, or easier way of understanding it. Graphs with symmetry about a specific line, specific axis, look the same when you replace, well, for the y-axis, it was x goes to negative x, and the x-axis, it was y goes to negative y. We see that here with the absolute value there. This is the absolute value of x minus 3. We replace x with negative x, and it's the same graph. I don't know if you can see that. It goes from a red line to a blue line, but they're identical. And notice we can do this up here with y equals negative x. Put that up here, put that up here. There's y equals x to the 4th, and I replace it with negative x in parentheses, and I get the same graph. Okay? So it's easier visually to see this replacement leads to symmetry. On a graph. Because it stays the same, because the graph remains the same. All right. And what if we replace both at the same time? At the same time and get the same graph. I'll give you some examples. Let's take a look at what's happening, and then we'll do the algebra. So I've got y equals x. And I've got negative y equals negative x. Notice I replace y with negative y and x with negative x. I get the same line. Let's do it with some other ones. Y equals x cubed. And negative y equals negative x cubed. Do that here. Same graph. Let's kick it up a notch. It should work. And negative y equals negative x raised to the 3rd power minus 3 times negative x raised to the 3rd power. So I did the same thing here with a much more complicated function. I replace x with negative x and y with negative y. And notice the graph is the same. So what's going on here? We do x to negative x and y to negative y. Let's look at just y equals x cubed. We have y equals x cubed, and I replace them both with negative. Get negative y equals negative x cubed. And if I cube negative x, that's the same thing as negative x cubed. And if I multiply both sides by negative 1, I get y equals x cubed, and I'm back to the beginning. When this happens, we call this symmetry about the origin. Okay? And what that means, I'm going to draw it by hand. I'll pause this and get it up a little bit longer. I'm going to do a big graph. We're just going to do y equals x cubed. If we start at the origin, and make an arrow to any point on the line. In the graph. Okay, so that's what I did here. Make an arrow the exact same length. But in the opposite direction. It will land on the graph. Now, if I had drawn these better, this would look good. This is a bad drawing. Arrows should be the same length. If I knew Desmos a little bit better, I would do it on there. That's the idea of symmetry about the x-axis. Graphs that have this, y equals x cubed. Hell, you just saw me do y equals x to the 5th minus 3x cubed. Does it matter that that's a 3? What if I change this to a 2? Same. What these have in common is all the exponents are odd. All exponents of x are odd. These are part of a set called the odd functions. So odd functions have this property. Are symmetrical about the origin. We have y equals f of x, and we do x equals negative x and y equals negative y. We take those, plug them in. You get negative y equals f of negative x, like that. If that gets us back to y equals f of x, we have symmetry about the origin. So odd functions, all the exponents are odd. What about if I do y equals negative x to the negative 1? Oops. See, the exponent is net odd and it still works. Odd functions, all the exponents are odd. In trigonometry, sine of x is odd. You'll see that. And you're going to see that cosine of x is even. Odd functions, all the exponents are odd. What happens if I have, we showed up here, x to the fourth and negative x to the fourth. What if I have plus x squared? Let's make it plus 3x squared. Negative x squared. Look at those two. As long as all the exponents are even, it's even. If we mix and match though, notice if I change this to x to the fifth, oops. It's not the same, is it? So when the graph is mixed, odd and even exponents, it doesn't work. A mix of odd and even exponents is neither. And which means there's no symmetry. This one actually looks like a reflection. Let's put these all together though. Okay, so back to y equals a f of bx minus h plus k. So let's look at y equals 2 times x minus 1 squared plus 3. If I match these up, I've got a equals 2, which was vertical stretching. H equals 1 and k equals 3. If I got rid of the 2, the negative 1, and the 3, this looks like a base graph of y equals x squared. So, how do we graph this? Move the vertex to HK, or center. I said vertex because it's parabola, to the point HK. Then what do we got going on? Delta x, delta y. And the only other thing, we've dealt with the h and the k, we have that too. So what about 2x squared? So plus or minus 1 plus or minus 2 leads to 2 and 4, or 1 and 4. This is 2 times delta y. Double it, that's 2 and 8. So I'm going to move my center to 1, 3. And then I'm going to go left or right 1. And up, not 1, but 2. And left or right 2, and up 8. There's a line there. So shift the graph over to HK, and then deal with the A and the B. Another way of doing this, and put up the same equation, y equals 2 times x minus 1 squared plus 3. Graph without the HK, y equals 2x squared, and then move all the points right H, up K. And if H is negative, it goes to the left. If K is positive or negative, it goes down. So what I mean by doing that, I'll show you. So the base graph for 2x squared is like this. And rather than drawing the line, I'm just going to put the points and then I'm going to move them all. HK is 1, 3. So I'm going to move every point right 1, up 3. 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 Then do the parabola. So plot the base points, then shift them all. Or shift the center and then do movement off of them. Or you just find the center. Or just center your table around x equals h. H here is 1. So I'll put 1 there, positive 1 there. I'll go left 2 and right 2. And then calculate 2 times x minus 1 squared plus 3. Put it in, negative 1 minus 1 is negative 2 squared is 4. 4 times 2 is 8, plus 3 is 11. 0 minus negative 1 is negative 1. Squared is positive 1. Times 2 is 2. Plus 3 is 5. 1 minus 1 is 0. That goes away. We just have the 3. If I put the 2 in, I should start getting a repeating thing like that. So that's another way. Just center your table around x equals h. And go a couple points left or right. Do a couple x less than, lower and greater. Okay. This is a good, this method always works. Okay. It always works to stick in values of x and plot and find out what the values of y are. The only reason I reckon the problem is you need to make sure you center around where x equals 0 in the normal graph. And we showed that before on the y equals x minus 3 squared when we translated it over. It screwed it up a bunch. So quick recap. We got y equals f of x. That's our base. If we add k to it, graph goes up k if k is greater than 0, down k if k is less than 0. If we look at having the h on the inside, graph goes right h if h is greater than 0, which makes this look like x plus h or x minus h. And graph goes left 0 or h if h is less than 0, and that looks like x plus h on the inside. Negatives in front, flip the graph. So C on them, or look at Desmos. I'll do it on Desmos real quick. Do y equals x minus 1 squared plus 2, and y equals negative x minus 1 squared plus 2. That's what I meant by putting the negative in front. Negative in front is the same thing as a equals negative 1. Take a look at these. Now, copy this. And watch what happens when I put a negative in front. It flips the graph upside down. Okay? Negatives in front of the graph, flip it upside down. Provide a quick little sketch here. The center is at 1, 2. That's that one. And that is it flipped over. It flips because of that negative sign. And this works if we've got some crazy things. Let's say the graph of y equals f of x looks like this. I've got a point at negative 4, 0. I've got a point at negative 2, 2. I've got a point at 0, 0. I've got a point at 1, negative 3. And let's say 3, 0. If we do, I don't even know what the equation is. If I do like a -2, all those points are going to shift down 2. So negative 4, 0 goes down to negative 4, negative 2. Negative 2, 2 goes down to positive negative 2, 0. 0, 0 goes down to negative 2. 1, negative 3 goes down to 1, negative 5. And 3, 0 goes down to 3, negative 2. All right. And that'll wrap up 2.7. It's a little bit of a long section, but there's a lot of stuff going on with graphing. MATLAB does have a couple problems like this where they give you the graph and they say which one of these is the correct graph for these types of translations. That's it for that section. Peace.